All right, let's dive into some linear algebra. You know, the math behind deep learning.
Yeah,
People find this stuff intimidating, but it's really not that bad.
right.
Honestly, it's like unlocking a secret language that makes deep learning so much clearer.
Yeah.
Today, we're breaking down Chapter 2 of this deep learning textbook.
Yeah.
It's designed for those of us who maybe haven't spent much time with linear algebra.
Right.
So think of this deep dive as your cheat sheet to understanding the most important parts of linear algebra for deep learning.
Yeah. And, a lot of the power of deep learning comes from applying these core concepts.
Okay.
And we're going to focus on building that intuition today.
Perfect. So let's start with the basics.
Sure.
What are the essential elements that we need to understand?
Well, first off, we have scalars, which are just individual numbers.
Okay.
Think 3, -5, 10.2.
Mm-hmm.
Your everyday numbers.
Okay.
Then we have vectors, which are lists of these numbers.
Okay.
You can think of them like coordinates on a map.
Okay.
Imagine you need to pinpoint the location of a coffee shop.
Okay.
You would need its latitude and longitude,
Right.
and maybe even altitude if it's on the 10th floor of a building.
Yeah.
That's your vector.
Okay. I see how vectors can represent something real.
Right.
So how do matrices fit into all of this?
So matrices, think of a matrix like a spreadsheet.
Okay.
Rows and columns of numbers,
Okay.
creating a grid.
Okay.
And they're essential for representing relationships between multiple things.
Okay.
So let's say you're tracking the sales of different coffee flavors at that coffee shop each day.
Okay.
Each row could be a different flavor.
Okay.
Each column a day of the week.
Mm-hmm.
And the cells would hold the number of cups sold.
Right.
That's your matrix.
Ah, okay.
Yeah.
So matrices are great for organizing more complex data.
Right.
And what about tensors? How do those fit in?
So you're on the right track.
Okay.
Tensors are essentially multidimensional arrays, capable of holding even more complex data than matrices.
Okay.
So imagine having sales data for multiple coffee shops across a city.
Okay.
You could represent that with a tensor where one dimension is flavor,
Yeah.
one is day of the week, and another is the shop location.
Yeah, okay, got it.
They're crucial for deep learning because they can represent things like images,
Right.
which are just grids of pixel values.
Right.
Or even sequences of data over time.
Okay.
Right.
So we've got our scalars,
Yeah.
vectors, matrices, and tensors.
Yeah,
But we can't just leave them sitting there, right?
Right.
We need to actually do something with them.
exactly.
So what kind of operations can we perform on these things?
One of the most important operations is matrix multiplication.
Okay.
Now, you might think we just multiply corresponding numbers in the grid, but
Yeah, back in high school, I remember matrix multiplication being a bit of a head scratcher.
yeah.
It's not that simple, is it?
It's more about the interaction between entire rows and columns.
Right.
Imagine each row in the first matrix
Okay.
is like a scanner sweeping across each column of the second matrix.
Okay.
Yeah.
Okay, so it's not just a single calculation, but it's like a whole bunch of interactions.
Precisely.
Okay.
Each entry in the resulting matrix
Mhm.
comes from a specific row-column scan.
Got it.
And it's this interaction that makes matrix multiplication so powerful for modeling relationships in data.
Okay.
And it also means the order we multiply matrices matters.
Right.
Flipping things around can change the result.
Right. A times B isn't always the same as B times A.
Exactly.
Unlike regular numbers.
Right.
I remember that causing some confusion back in the day.
Yeah.
Now let's say we have this equation with matrices.
Okay.
AX equals B.
Okay.
You have a matrix A,
Yeah.
a mystery vector X,
Mm-hmm.
and a known vector B.
Okay.
Think of it like a locked box. You know, the box is design A
Right.
and what's inside B.
Yeah.
But you need the key X to unlock it. That's where the concept of an inverse comes in.
Right.
So if we can find this inverse of matrix A, we can essentially unlock the equation
Exactly.
and find that unknown X.
It's like reversing the operation of A.
Okay.
However, finding this inverse isn't always easy.
Right.
And in some cases, it might not even exist.
Oh.
And that's where things get interesting.
Okay, so it sounds like the existence of this inverse
Yeah.
is a pretty big deal.
Right.
What makes a matrix invertible?
Well, it boils down to this idea of linear dependence.
Okay.
Think of it this way.
Okay.
You're trying to navigate a city,
Okay.
and you're given a set of directions.
Okay.
Those are your vectors.
Okay.
What if some of those directions are redundant?
Okay.
Like you're told to go north for a block, then turn east, and then go north again for that same block.
Okay.
You ended up going north twice,
Right.
which is kind of pointless, really.
Yeah, that seems like an inefficient way to give directions.
Exactly.
So you're saying a matrix is invertible only if all of its directions
Yeah.
or vectors are unique.
That's a great way to put it.
Okay.
The columns of a matrix need to be linearly independent,
Okay.
meaning none of them can be expressed as a combination of the others.
Okay.
If they are dependent, it's like having those redundant directions.
Okay.
They don't add any new information, and the matrix won't have an inverse.
Got it. So linear independence is key here.
Right.
But I'm imagining that some matrices are more independent than others.
Yeah.
So how do we actually measure how much unique information a matrix holds?
That's a fantastic question, and it leads us to the concept of span.
Span, like
Yeah.
how far something stretches.
Exactly.
Okay.
The span of those direction vectors
Mm.
is all the possible locations you could reach by combining them in various ways.
Okay.
Think of it like drawing a map
Okay.
of all the places you could get to using those directions.
Okay.
If you only have 2 independent directions, your map might be limited to a flat plane.
Okay.
But if you have 3 independent directions,
Okay.
suddenly your map expands to encompass a whole 3D space.
Oh, wow.
Yeah.
So I'm starting to see how this relates to our invertible matrices.
Right.
If a matrix has enough linearly independent columns,
Yeah.
its span can cover a larger space,
Yeah.
giving us more freedom to move around.
Exactly.
Or in this case, find solutions. I
Yeah.
get it.
And the dimension of that space
Okay.
is directly related to the rank of the matrix,
Okay.
which essentially tells us how many truly independent directions it provides.
Got it.
A full rank matrix,
Okay.
where the rank equals the number of columns,
Okay.
has the largest possible span,
Mm-hmm.
and is definitely invertible.
So full rank matrices are the superstars of linear algebra.
You could say that.
Okay.
But even if a matrix isn't full rank,
Okay.
we still have ways to deal with it,
Right?
using clever tools like the Moore-Penrose pseudo-inverse,
Okay.
which we'll get to later.
Okay.
But first, let's talk about how we can measure the size of our vectors.
Okay.
It's not as straightforward as you might think.
Okay, so now we're talking about vector measurements.
Right.
I'm assuming it's not just length, right?
Right.
Because vectors can be in multiple dimensions.
Exactly.
Things get a bit trickier.
In linear algebra, we use something called norms
Okay.
to quantify the size or length of a vector,
Okay.
but there are different ways to do it,
Okay.
depending on what aspect of size you want to emphasize.
All right, hit me with these different norms.
Okay.
What kind of vector sizes are we talking about?
Well, one common norm is the L2 norm,
Okay.
or Euclidean norm.
Okay.
This is your classic Pythagorean distance.
Okay.
Imagine a right triangle,
Okay.
where the vector is the hypotenuse.
Okay.
The L2 norm is like measuring the length of that hypotenuse.
Okay. That one feels intuitive, like actually measuring the distance.
Right.
What other norms are there?
We have the L1 norm, which simply adds up the absolute values of each component in the vector.
Okay.
Think of it like calculating the total distance traveled
Okay.
if you were to walk along each dimension separately.
Interesting.
Yeah.
So if one component was -3, we would count it as moving 3 units.
Exactly.
Okay.
The L1 norm doesn't care about direction,
Okay.
just the total magnitude of each component.
Okay.
And this property makes it really useful in deep learning
Okay.
for encouraging something called sparsity.
Sparsity.
Yeah.
What is that?
Meaning we want lots of zeros in our vectors.
Okay.
Yeah.
Wait, why would we want a bunch of zeros in our vectors?
It might seem counterintuitive, but sparsity can actually help us build simpler,
Okay.
more robust models.
Okay.
Think of it like decluttering a room.
Okay.
Getting rid of unnecessary stuff
Okay.
can make it easier to find what you need
Right.
in deep learning.
Yeah.
Sparsity can help prevent something called overfitting,
Overfitting.
where the model becomes too specialized to the training data
Okay.
and doesn't generalize well to new data.
Right.
Yeah,
So sometimes less is more.
exactly.
Fewer non-zero values can actually make our model stronger.
Right.
I get it.
Yeah.
So I've got L1, L2.
Yep.
What other norms are in our toolbox?
Well, we also have the L infinity norm,
Okay.
sometimes called the max norm.
Okay.
It's the simplest of the bunch.
Okay.
It just picks the largest absolute value among the vector components.
So if one component is 10
Yeah.
and the others are smaller,
Yeah.
the L infinity norm is just 10.
Yes,
Seems pretty straightforward.
it is.
Okay.
And don't forget about the Frobenius norm.
Okay.
This one applies to matrices,
Okay.
and it's kind of like the L2 norm.
Okay.
But for all the entries in the matrix,
Okay.
it's a way of measuring the overall magnitude of the matrix.
Got it.
Yeah,
We've got a whole arsenal of norms now.
we do.
L1,
Yep.
L2,
Yeah.
L infinity.
Right.
and Frobenius.
Yeah.
It's like choosing the right measuring tape depending on what kind of size we're interested in.
Exactly.
And
And these different norms play important roles
Yeah.
in various machine learning algorithms,
Okay.
especially when it comes to things like regularization,
Okay.
which helps prevent overfitting and improves model performance.
All right. So we've tackled the building blocks,
Yeah.
operations, inverses, and even how to measure these things.
Right.
What else is there?
Well, now that we have a grasp of the basics,
Okay.
let's delve into some special types of matrices and vectors
Right.
that have unique properties
Okay.
and make our lives a lot easier in deep learning.
Bring on the special matrices.
All right.
What kind of superpowers are we talking about?
But one type is diagonal matrices.
Okay.
These are like the clean freaks of the matrix world.
Okay.
They have non-zero entries only along the main diagonal,
Okay.
from the top left to the bottom right,
Yeah.
with everything else being zero.
So like a perfectly organized line of numbers cutting across the matrix.
Exactly.
Okay.
They're great because operations with them become super efficient.
Okay.
Multiplying a vector by a diagonal matrix
Okay.
is simply scaling each component of the vector by the corresponding diagonal entry.
Okay.
Yeah.
That's handy.
It is.
Any other special matrices we should know about?
Definitely.
Okay.
There are symmetric matrices
Okay.
where the entries are mirrored across the main diagonal.
Okay.
Imagine folding the matrix in half along that diagonal.
Okay.
If the numbers match up perfectly, it's symmetric.
Okay.
These often pop up when we're dealing with pairwise relationships that don't depend on order,
Okay.
like distances between cities.
Right, because the distance from city A to city B is the same as city B to city A.
Right, exactly.
Okay. Okay. Makes sense.
So,
diagonal and symmetric matrices have these neat properties
yeah,
that make calculations simpler.
Right.
What about vectors? Are there any special ones?
absolutely.
Okay.
There are unit vectors,
Okay.
which are like the compass directions
Right.
of the vector world.
Okay.
They point in a specific direction,
Okay.
but have a length of one.
Okay.
Think of them as providing just the directional information without any magnitude attached.
Okay, so unit vectors are all about direction, no size baggage.
Exactly.
What about those orthogonal vectors I keep hearing about?
Orthogonal vectors are like the perfectly perpendicular vectors.
Okay.
They form 90-degree angles with each other,
Okay.
like the axes in a coordinate system.
Okay.
And if these orthogonal vectors also happen to be unit vectors,
Okay.
meaning they have a length of one,
Okay.
we call them orthonormal.
Orthonormal.
Yeah.
It's like the ultimate combination of direction and precision.
It is.
But how do these special vectors relate to matrices?
Well, imagine a square matrix
Okay.
where all the rows and columns are orthonormal vectors.
Okay.
This, my friend, is an orthogonal matrix,
Oh, okay.
and they're like the superheroes of linear transformations
Huh. Okay.
because they preserve lengths and angles.
Preserve length and angles. That sounds pretty important.
It is.
Why is that such a big deal?
Well, think about rotating an object in space.
Okay.
You don't want it to get distorted
Right.
or stretched in the process,
Mm.
right?
Right.
Orthogonal matrices ensure that the object maintains its original shape and size,
Okay.
even after the transformation.
Wow. That's incredibly useful.
Yeah,
And I have a feeling these orthogonal matrices have some other cool tricks up their sleeve.
you bet. One of the most amazing things about orthogonal matrices
Okay.
is that their inverse is simply their transpose.
Wait, hold on.
Yeah.
Transpose, that's where we flip the rows and columns.
Yeah.
So to invert an orthogonal matrix, we just swap the rows and columns.
You got it. It's
Yeah.
a super convenient property.
Wow.
That makes working with them computationally much easier. And this ties into a fascinating concept called eigendecomposition.
Okay, eigendecomposition sounds intense.
Yeah.
We've covered a lot of ground already.
We have.
From basic building blocks
Yep.
to special matrices
Yeah.
and even vector norms.
Uh-huh.
I'm ready to delve into this hidden DNA of matrices.
Right.
What can you tell me about this eigendecomposition?
Well, first imagine a matrix
Okay.
as a transformation
Okay.
that stretches or compresses space in certain ways.
Okay.
Eigendecomposition allows us to find the specific directions
Okay.
that remain unchanged after this transformation,
Okay.
except for maybe a scaling factor.
So it's like finding the lines of least resistance.
Exactly.
Okay.
Those special directions
Yeah.
are called eigenvectors.
Okay.
And the scaling factors are called eigenvalues.
Okay.
They're like the matrix's fingerprints,
Okay.
revealing its fundamental characteristics.
This is starting to sound like we're getting into the really powerful stuff.
We are. But let's save that deep dive into eigendecomposition for part 2 of our linear algebra adventure.
Okay.
I think we've given our listener plenty to chew on for now.
I agree. Okay, so we left off on this cliffhanger about eigendecomposition, the hidden DNA of matrices.
Right.
I'm ready to unlock this mystery.
Right.
What can you tell me about it?
Let's untangle this DNA.
Okay.
Remember how we were picturing a matrix
Yeah.
as a transformation that stretches or squishes space?
Yeah, like some kind of mathematical funhouse mirror.
Exactly. Now imagine there are certain directions
Okay.
in this space
Okay.
that when transformed by the matrix only get scaled up or down,
Okay.
but don't change their fundamental direction.
So they're like the unbreakable lines in that funhouse mirror, just getting longer or shorter?
That's a great way to visualize it.
Okay.
Those special directions are called eigenvectors,
Okay.
and the factor by which they get scaled
Yeah.
is called their corresponding eigenvalue. They're like the matrix's signature, revealing how it prefers to transform space.
Okay, I'm starting to get the concept, but why are eigenvectors and eigenvalues so important?
Right.
What kind of secrets do they unlock?
Well, for one thing,
Okay.
they can tell us a lot about the stability and behavior of dynamic systems.
Okay.
Think about a population model
Okay.
where a matrix represents how the population changes from one generation to the next.
Okay.
The dominant eigenvector,
Okay.
the one with the largest eigenvalue,
Okay.
will tell you the long-term trend of the population, whether it's growing, shrinking, or stabilizing.
Ah, so the dominant eigenvector is like the trendsetter for the system.
Precisely.
Okay.
And this concept isn't just limited to populations.
Right.
You can apply it to all sorts of systems,
Okay.
from the spread of information on social networks to the behavior of financial markets.
Wow. Okay.
Yeah.
So this is powerful stuff.
It is.
But is eigendecomposition only useful for analyzing these systems over time? What about other applications?
Oh, there are tons.
Okay.
Take Google's PageRank algorithm, for example.
Okay.
It uses eigendecomposition
Okay.
to determine the importance of web pages
Okay.
based on the link structure of the internet.
Right.
The eigenvector, corresponding to the largest eigenvalue, essentially represents the ranking of all web pages based on their influence.
So that's how Google figures out which pages are the most authoritative and relevant?
Right.
Pretty impressive.
Yeah.
But hold on.
Yeah.
Earlier you mentioned that eigendecomposition isn't always possible.
Right.
What kind of matrices can't be broken down this way?
Not every matrix can be decomposed into real valued eigenvectors and eigenvalues.
Okay.
But for many applications in deep learning,
Okay.
especially those involving image processing and natural language processing,
Right.
we often work with something called symmetric matrices.
Symmetric matrices.
Yeah.
Those were the ones that were like mirror images across the diagonal, right?
Exactly.
Yeah.
And those are guaranteed to have a nice, clean eigendecomposition.
So they're the well-behaved matrices.
You could say that,
Okay, cool.
but what happens when we're dealing with matrices that aren't symmetric?
Okay.
Or even worse, rectangular ones.
Yeah.
That's where singular value decomposition comes in.
SVD, it's like eigendecomposition's more versatile cousin.
You could say that.
Okay.
SVD is a more general form of eigendecomposition.
Okay.
It can be applied to any real matrix,
Okay.
even those that are non-square.
Okay, so it's the more powerful all-purpose tool.
Yeah.
But how does it work?
Well,
Does it also involve finding special vectors and values?
it does.
Okay.
Similar to eigendecomposition,
Okay.
SVD breaks down a matrix into 3 component matrices:
Okay.
U, sigma, and V transpose.
Okay.
U and V are orthogonal matrices.
Right. Those were the ones whose inverse is just their transpose.
Right.
Very handy.
Sigma is a diagonal matrix,
Okay.
and its entries are called singular values. They're analogous to eigenvalues in eigendecomposition,
Okay.
but they represent the magnitudes of stretching or shrinking
Okay.
that the original matrix performs
Okay.
in different directions.
So the singular values tell us how much the matrix scales things up or down.
Right.
What about those U and V matrices?
Yeah.
What role did they play?
Those contain these singular vectors,
Okay.
which are like the eigenvectors we talked about earlier.
Okay.
The columns of U are called left singular vectors,
Okay.
and they tell you the important directions
Okay.
in the output space,
Okay.
while the columns of V are called right singular vectors
Okay.
and tell you the important directions in the input space.
So it's like SVD is giving us a roadmap
Yeah,
of how the matrix transforms space,
exactly.
showing us the most important directions for both the input and output.
Precisely.
Okay.
And this roadmap is incredibly useful for a whole bunch of applications,
Okay.
from image compression to recommendation systems to natural language processing.
Hold on, image compression.
Yeah.
How does SVD help us compress images? I thought that was all about some fancy algorithms.
Well, those algorithms often rely on SVD under the hood.
Okay.
So imagine representing an image as a matrix,
Okay.
where each entry corresponds to a pixel value.
Okay.
SVD can decompose this matrix and reveal the most important components
Okay.
that capture the most significant visual information.
Okay.
We can then discard the components with small singular values,
Okay.
essentially throwing away the less important details,
Right.
and reconstruct the image using only the dominant components.
So it's like SVD helps us find a compressed version of the image
Exactly.
that still retains most of the visual features.
Right.
That's really cool.
Yeah.
But you mentioned earlier
Yeah.
that SVD was particularly helpful when dealing with non-square matrices.
Right.
What's the challenge with those?
Remember how we talked about the inverse of a matrix
Yeah.
being like the key to unlocking an equation?
Right.
Well, non-square matrices
Yeah.
don't have a traditional inverse.
Oh.
It's like trying to fit a square peg into a round hole.
Right, that won't work.
Exactly.
So how does SVD help us deal with these uninvertible matrices?
It introduces us to the Moore-Penrose pseudo-inverse.
Okay.
Think of it as a generalization of the inverse
Okay.
that can be applied to any matrix,
Okay.
even those that are non-square.
So the pseudo-inverse is like the master key
You got it.
that can open those tricky locks
Yeah.
that regular inverses can't.
It might not be a true inverse,
Right.
but it allows us to find solutions,
Okay.
or at least the closest approximations,
Right.
to linear equations involving those troublesome non-square matrices.
Okay, so it's still really useful.
Very useful.
SVD is definitely earning its superhero cape.
It is.
We've covered a lot of ground with eigendecomposition and SVD,
Yeah.
uncovering those hidden structures
Right.
within matrices.
Yeah.
What other tools do we have in our linear algebra toolbox?
Well, let's not forget about the trace operator.
Trace operator. That doesn't sound too intimidating.
It's not.
What's it all about?
It's simply the sum of the diagonal elements of a square matrix.
Okay.
It's like adding up the values along that main street of the matrix,
Okay.
from top left to bottom right.
So it's just a sum.
It is.
Why is that so special? What can we learn from adding up those diagonal numbers?
Well,
Yeah.
it turns out the trace has some really neat properties.
Okay.
For one,
Yeah.
it's invariant to transposition,
Okay.
meaning the trace of a matrix is the same as the trace of its transpose.
So it doesn't matter how we slice the matrix, the trace remains the same.
Exactly.
Okay.
And this can be helpful when simplifying complex expressions
Okay.
and proving certain mathematical theorems.
So it's a handy little tool.
It is.
Okay.
Plus, you can use the trace operator to express the Frobenius norm of a matrix.
Ah, so the trace connects back to other concepts we've learned.
Right.
It's like we're building this interconnected web of linear algebra tools.
Exactly. And speaking of interconnectedness,
Yeah.
let's not forget about the determinant.
The determinant.
Yeah.
That always sounded kind of mysterious to me.
It is kind of like a code.
Okay.
It's a single number.
Okay.
That encapsulates a lot of information about a square matrix.
Okay.
Think of it as a measure of how much the matrix scales space.
Scale space.
Yeah.
Does it tell us how much a matrix stretches or shrinks things?
Exactly.
Okay.
If the determinant is 1,
Okay.
it means the matrix preserves volume,
Okay.
like a rotation
Okay.
or reflection that doesn't change the size of the object.
Okay.
If the determinant is greater than 1,
Okay.
it means the matrix expands space,
Okay.
making things bigger.
Mm-hmm.
And if it's between 0 and 1,
Okay.
it means the matrix shrinks space,
Okay.
making things smaller.
Okay.
Yeah.
So the determinant gives us a sense of the matrix's scaling power. What happens if the determinant is 0?
A determinant of 0 is a special case.
Okay.
It means the matrix collapses space
Okay.
along at least one dimension.
Okay.
Imagine squishing a 3D object down into a flat plane.
Okay.
That's what a matrix with a determinant of 0 would do.
So it's like the matrix is losing some of its dimensions.
It is.
Okay.
And it has important implications.
Okay.
A matrix with a 0 determinant is singular,
Okay.
meaning it's not invertible.
Okay.
It's like that squished object.
Oh.
You can't unsquish it back to its original form
Right.
because some information has been lost.
Ah, I see the connection.
Yeah.
Invertible matrices
Yeah.
need to have a non-zero determinant.
Right.
Meaning they can't collapse space and lose information.
Exactly.
It's all coming together.
And this concept of the determinant being linked to invertibility
Yeah.
is crucial for understanding how linear algebra plays a role in solving systems of equations
Okay.
and analyzing data.
Mm.
But to really see these concepts in action,
Okay.
let's dive into a practical example. Principal component analysis,
Right.
or PCA.
PCA, I've heard that thrown around a lot in data science and machine learning.
Yeah,
It's a dimensionality reduction technique, right?
you got it.
Okay.
PCA is a classic example of how linear algebra concepts can be used to make sense of large, messy data sets.
Okay.
It's all about finding the most important directions of variation in the data,
Okay.
the directions that capture the most information.
Okay.
Yeah.
So it's like identifying the main storylines.
That's a great way to put it.
Okay.
And guess what? Those main storylines
Yeah.
are represented by eigenvectors.
Oh, cool.
Remember how they represent the directions that only get scaled by a matrix
Right.
without changing their fundamental orientation?
So PCA is using eigenvectors to find the most important directions of variation in the data.
Yes.
But how does that actually reduce the dimensionality?
Well, once we've identified
Yeah.
those important directions,
Okay.
we can project the original data
Okay.
onto a lower dimensional space spanned by those eigenvectors.
Okay.
It's like taking a 3D object and casting its shadow onto a 2D surface.
Okay.
You're losing some information,
Yeah.
but the shadow still captures the essence of the object's shape.
I see. So PCA is essentially finding a shadow of the data
Exactly.
that retains most of the information, but in fewer dimensions.
Right.
That's pretty clever.
It is.
Okay.
And the key to this whole process is finding those eigenvectors
Okay.
that represent the most important directions of variation.
Right.
And how do we find them? You guessed it, eigendecomposition.
Wow. So eigendecomposition is at the heart of such a practical technique like PCA.
It really is.
That's amazing.
And this is just one example of how linear algebra provides the foundation for countless algorithms and techniques in machine learning and data science.
Okay, so we've gone from scalars and vectors to matrices and tensors,
We have.
explored inverses and determinants,
Yeah.
and even delved into the world of eigendecomposition and SVD.
It feels like we've climbed a whole mountain of linear algebra knowledge.
We have, and the view from up here is pretty amazing.
It is.
You can really see how all of these concepts come together
Yeah.
to solve real-world problems. It's
Yeah.
been a real eye-opening journey.
Good. I'm glad.
But I have a feeling there's even more to explore.
There is.
What else awaits us in part 3?
Well, we've laid the groundwork. Now it's time to put it all together.
Okay.
We'll connect these concepts back to the world of deep learning
Okay.
and explore how they power some of the most advanced algorithms used today.
So stay tuned for the final part of our linear algebra adventure. All right, we've scaled that linear algebra mountain, explored those hidden structures, and even dabbled in dimensionality reduction.
Right.
But how does all of this math wizardry actually translate to the world of deep learning?
Yeah.
I'm ready to see how it all connects.
That's the exciting part.
Okay.
It's like we've gathered all the ingredients, and now it's time to bake that delicious deep learning cake.
I love that analogy. So what are some of the key areas in deep learning where linear algebra really shines?
Well, it all starts with the basic building blocks of neural networks.
Okay.
Neurons.
Okay.
You can think of each neuron
Okay.
as performing a simple linear algebra operation.
Okay.
It takes a set of inputs,
Yeah, okay.
multiplies them by a set of weights,
Okay.
adds a bias term,
Okay.
and then applies an activation function.
Wait, so each neuron is basically doing a weighted sum of its inputs,
Exactly.
which is just a dot product, right?
Yes.
That's linear algebra in action.
Right. And those weights and biases,
Yeah.
those are essentially the parameters of the neuron
Okay.
that get adjusted during training.
Okay.
Remember how we talked about solving linear equations
Yeah.
to find unknown values?
Right.
Well, training a neural network
Yeah.
is essentially solving a giant system of linear equations
Okay.
to find the optimal weights and biases
Oh.
that minimize the error of the model.
Wow. So each neuron is like a tiny linear algebra machine.
Yeah,
And the whole network is this massive interconnected system of equations.
that's a great way to think about it.
Wow. Okay.
And as the network learns,
Yeah.
those weights and biases are constantly being updated
Okay.
using techniques like gradient descent.
Gradients, those sound familiar from calculus.
All right.
How do they fit into the linear algebra world?
So think of a gradient as a vector
Okay.
that points in the direction of the steepest descent of a function.
Okay.
In deep learning, we want to find the minimum of a loss function,
Okay.
which represents the error of our model.
Okay.
So we use the negative gradient to move our weights and biases
Okay.
in the direction that reduces the error.
So it's like we're navigating a mountainous landscape,
Yeah,
and the gradient is like our compass,
right.
guiding us towards the lowest valley,
Exactly.
which represents the best set of parameters
Yeah.
for our model.
And calculating those gradients efficiently
Yeah.
for these complex neural networks
Okay.
requires some clever linear algebra tricks.
Okay.
Remember those special matrices we talked about?
Right, like diagonal and orthogonal matrices?
Exactly.
So they're actually useful for deep learning, too.
They pop up all over the place,
Okay.
especially when it comes to optimizing performance
Okay.
and making training more efficient.
Okay.
For example, techniques like batch normalization,
Okay.
which help stabilize training and improve accuracy, often involve manipulating diagonal matrices.
Oh, okay, so they weren't just mathematical curiosities. They actually have real-world applications.
Yeah.
That's cool.
Yeah.
And don't forget about eigendecomposition and SVD.
Yeah.
They play a pretty important role, too, right?
A key role
Okay.
in understanding and manipulating the representations learned by deep neural networks.
Wait, so they're not just about analyzing static matrices?
Right.
They're actually used to analyze what the network is learning.
Absolutely. For example, techniques like principal component analysis,
Right.
or PCA,
Yeah.
which we discussed earlier, can be applied to the activations of neurons in a deep network
Okay.
to visualize what features the network is learning to detect.
So it's like we're using PCA to peek inside the brain of the network.
Exactly.
Okay.
And SVD can be used to analyze the weights of a trained network
Okay.
to understand the relationships between different neurons and layers.
Okay.
This can help us identify redundant or unimportant connections, leading to more efficient and interpretable models.
Wow, it's like linear algebra is giving us this X-ray vision into the inner workings of deep learning.
It really is, and it's not just about analysis.
Okay.
Linear algebra also powers some of the most cutting-edge deep learning architectures,
Okay.
like convolutional neural networks,
Okay.
or CNNs,
Right.
and recurrent neural networks, or RNNs.
CNNs and RNNs, those are the big ones for image and text processing, right?
They are.
How does linear algebra fit into those?
CNNs, which are amazing at tasks like image classification and object detection. Use convolutional operations,
Okay.
which are essentially sliding dot products between a filter matrix and the input image.
Wait, so those convolutions, which sound super complex,
Yeah,
are actually just a bunch of dot products.
they are.
That basic linear algebra operation, that's mind-blowing.
It is.
Okay.
And RNNs, which excel at processing sequential data,
Okay.
like text and speech,
Yeah.
rely on matrix multiplications to update their internal state as they process each element in the sequence.
So no matter how complex these deep learning architectures get,
Yeah,
at their core, they're still relying on those fundamental linear algebra operations.
exactly. Linear algebra provides the mathematical language
Okay.
and the computational tools
Okay.
that make deep learning possible.
It's amazing how these seemingly abstract concepts we explored,
Yeah.
like eigenvectors, norms, and determinants, are actually the driving force behind some of the most powerful technologies shaping our world.
It really highlights the beauty and power of mathematics.
Yeah.
Understanding linear algebra not only gives you a deeper appreciation for how deep learning works,
Right.
but also empowers you to develop new algorithms
Okay.
and push the boundaries of what's possible.
I'm so glad we did this deep dive.
Me too.
I feel like I've unlocked this whole new level of understanding about deep learning.
I'm glad to hear that.
Okay.
And remember, the journey doesn't end here.
Right.
Keep exploring, keep asking questions,
Okay.
and keep that linear algebra toolbox handy as you delve deeper into the world of deep learning.
Absolutely. And to our listeners out there, I encourage you to do the same.
Yes.
Explore further and see those linear algebra connections come alive
Yeah.
in this exciting world of deep learning. Thanks for joining us on this deep dive.